The concept for e-part trade is basically, in my opinion, there's a big hole in the internet. So the internet started many years ago, but there's never been an online business community for racers on the World Wide Web. The need for e-part trade is actually quite obvious. Basically, people in the business of auto racing need a place online to hang out and get their problems solved.
It's extremely simple for a buyer or for a supplier to interact on the platform. The first thing you need to do is sign in, which is free. And the second thing is, when you see a product that you're interested in, all you need to do is click on request more information. If it's a company, you click on request more information, and then from there, it is forwarded directly to the buyer or to the supplier.
You can go to epartrade.com, you become part of a community of businesses in racing, and it makes sourcing products much easier than just on the internet or using Google.
At e-part trade, there is no e-commerce. It's literally a connection just like at a trade show. So now, any time of the year, a buyer could reach out to a supplier through an email.
More than that, it's a place to go just to keep current every day. So it's a good place to start your workday in your racing business or in your offices of your professional race team. And you know you're current when it comes to new technology, industry news, technical papers, technical videos, all of that and more. We're not looking for a million hits per day. All we want is people who are really the volume buyers of racing products in the racing industry to be part of the little world of e-part trade. We have racing businesses participating from around the world. So you get suppliers from around the world, you get buyers from around the world.
E-part trade really eliminates having to travel, closing down your shop. Now you have a place to showcase globally your racing product and technology.
Good morning from California, and welcome to Race Industry Now, the technical and business webinar series from e-part trade, presented to you by ARP and Performance Plus Global Logistics. This is episode 226, and we are going to be talking cryogenics with WPC Treatment, our very dear friend of us, who is bringing a very special guest with him. And I'm going to let Mr. Brad Gilly introduce our guest. So with me this morning are Judy, the co-founder of e-part trade, and our terrific host, Brad Gilly. Judy?
Thank you, Francis. Good morning, Brad. And thank you, everybody, for joining us today. You know, we have such a strong registration of attendees today, a whole bunch of engine builders and suppliers on today's webinar watching, that I thought I'd take this moment to kind of alert everybody that we are now working, confirming all our industry speakers, setting up our schedule of suppliers for the third annual Race Industry Week, which I cannot believe. And it's this November 28th through December 2nd. So on to you, Brett.
Well, thank you very much, Judy, and thank you, Francis. Really appreciate it, and really looking forward to today's webinar as well, because I think we're going to learn a lot of fascinating things, and definitely, I think we're going to spend a fun hour here. As always, I do want to remind you, if you have a question throughout the webinar, feel free to type it into the chat, and we'll get as many of those questions as we can to our two panelists here and try and answer everything that we can about really this amazing and fascinating technology. Our panelists today are Izumi Ogawa, the president of WPC Treatment, and Benzion Ben-Ami, the president of CTP. And today's title, Deep Cryogenic Processing, Myths and Facts. And gentlemen, welcome. We appreciate both of you being here today.
Thank you.
All right, Benzion, let me just start with you first of all, and give us an overview about the origins of this technology and some of the things that we're going to be talking about here today.
Absolutely. The origins of technology are a little foggy, but years ago, Swiss watchmakers noticed that brass ingots were machining a lot better when they were traveling through the Alps in the wintertime. So they used to put brass ingots into the snow for a couple of seasons to season them, per se. And from there, in the early 30s up until mid to late 30s, there was a lab in Germany that was developing cryogenics by the use of liquid nitrogen, and basically the same technologies we're using today. And that's basically the origins. After the war, a lot of this technology went deep underground into the aerospace industry. It was on a need-to-know basis. And And we've been trying to commercialize it since 1981, believe it or not.
That's fascinating. Izumi, if you would talk a little bit about the technology, and maybe let's talk about how this actually goes beyond heat treating and how it really can improve products and metals.
Good morning. We started WPC treatment business in 2005. And since then, we are providing metal surface treatment, WPC, which will improve the fatigue strength and also reduce friction by improving the oil retention of metal parts. I met Benchon 3 years ago, and I knew cryogenic treatment when I was in Japan. It was used in many industries. So I know it works. And one Japanese famous company use cryogenic treatment, heat treatment company use cryogenic treatment to improve the strength of the material. So I was familiar with cryogenic treatment, but I met Benchon, and he knows a lot of knowledge. He has a lot of knowledge about cryogenic treatment, and so that's why we partners with him, and we'd like to provide WPC and cryogenic treatment to racing industry to make more happy customers.
Happy customers are a really good thing. Benzion, when it relates to more specifically our audience here today, and that would be the automotive industry and the racing industry, I know there are a lot of parts and pieces that go into race cars and engines and blocks and camshafts and just a lot of different things that really cryogenic treatment can be a huge asset to. Can you tell us about some of that?
Sure. Cryogenic treatment actually isn't just what some people associate it with as a hardening process, converting in ferrous metal austenite to martensite, and that's all true. But when you make a part more evenly hard, and I'm talking about any metal part, even some composites and plastics, you're only as good as your weakest link. And when you can repair those weak links, and when your grain structure is a lot better, a lot more uniform, the part performs at its optimum. So pistons, conrods, any internal component, any component that sees a lot of stress, pistons, piston bores, heads. We did a lot of research with Marquette University on coil springs and the reduced fatigue life in coil springs. I got into discussing long-term, how should I say this, arrangements with a big freight company, because one of their fleet service managers used cryogenics on his 6,000 horsepower drag car. And he said that he got 7 times the life out of the coil springs. Now, things have moved on since then. I think metallurgy's moved on. There's a lot better techniques, better heat treatments. So we're seeing, you don't tend to see 7 times the life out of a component anymore, but we do see 2, 3, 4, or 5 times the life. It all depends on the use and how much stress the part goes through.
Yeah, and when you talk about that and what it can do and the benefits and all of that, and we all know as racers we want the lightest and the fastest and the best parts and everything, but we also need them to last and make sure that we don't break down. You mentioned the research into this. Can you speak more of that, either you, Benzion, or Izumi, about the research that goes into it and what has been found? Right.
So there is currently, if I was to guesstimate, because we look at a lot of research. It's mostly done in Asia and other countries, but there's probably around 1,500 to 2,000 different white papers out there that show the benefits of cryogenic treatment. And it's mainly done for industry, right? So we've applied it to different industries, but resistance welding electrodes, milling tools, et cetera, et cetera. And it's done to show the effects of cryogenic treatment. Izumi and I also quite frequently experiment with clients with practical results. And so instead of getting a lab to do XRD and all kinds of really deep coupon-based research, we do practical results. And we found some great success by mixing time temperatures and getting some great results. And it's not a one treatment fits all. Every alloy likes different temperature hold times, different ramping up, ramping down times, different temperatures even. You don't necessarily always have to go to negative 310 like we do to achieve those results. Sometimes you tend to go shallower and get an incredible result where at negative 300 or below doesn't give you those results.
If this is something that I'm interested in, let's say, are we talking like small batch type things, or if I'm a mass producer of parts and pieces, how does all of that work as far as like what can be done, the time frame and all of that?
Right, so we have a 7-day turnaround time, strict. Sometimes it's a little bit less, but we ask for 7 days in case your parts arrive in the middle of other batches. Basically, we can handle up to 2,000 pound payload at a time. We're about to actually produce 2 more machines, so we'll have a total of 3 machines that can handle that much. Small parts, we can handle enormous amounts. The payload of the machine is a 33-inch diameter by 50 inches deep, so we are able to load a lot of small parts. We do complete race cars. We can do up to, I think we've tried, I don't know, about 2.5 to 3 complete engines at a time. So the turnaround time is pretty good compared to what you see in other, even coatings. We're able to turn things around fairly quickly and take a lot at one time.
That's pretty fascinating. When you talk about increasing performance and with this technology, and let's say we're talking to some engine builders or race car team owners or people who are out there doing their own thing, how do you use the technology to increase the performance?
Well, so there's another element that's seldomly talked about, and this gave me a great idea, and we did some experiments. We saw research that was done some years back on the reliability of machinery when there's reduced harmonics and vibrations, and everybody knows vibration kills. So when you treat entire rotating assemblies, dare I say even axles and rims, which we do as well, you tend to see a lot less harmonics. Those harmonics rob you of horsepower and also reliability. So this is something that we know works, and one of the reasons that works is because when you have a part that's rotating at 2,000, even 1,000 RPM, and it has soft and hard spots, which is very typical even after great heat treat. As it reciprocates, it's throwing off different weight by its volume as it reciprocates. And so if you're making everything a lot more evenly hard, it vibrates a lot less, even on an axle that's only 1 inch thickness or in diameter.
Oh, wow. And in doing this and, looking through your website, Bención, and a lot of the great information that's on there, talking about how cryogenics actually, changes the crystalline structure and keeps things more in line. Can you talk a little bit more about that, about the advantages or how that helps?
Right. So there's some theories out there, and then there's some proof. We don't know everything, right? And that's why a lot of times we put together we do a lot of practical testing with companies to find out what works best. But we've done so much over the years, and we have a lot of experience. What happens is that at those extreme temperatures, people would think that everything is, solidly frozen, but there is movement, and there is movement in the crystalline structure. And the more symmetry and alignment there is in the crystalline structure, the better the performance is. So you're starting on the nanoscale, going up to the grain structure, and then up from there. What we also see in cryogenics, and this is something very common, in alloys, you get redistribution of alloying elements. So you're spreading out the alloying elements better throughout the piece. That gives you a better mix per se. And you also see in the boundary layers, if no one's ever looked into an alloy, there are boundary layers between the different metals that are combined, and there's a stitch layer. You actually repair a lot of that stitch layer, and you get much better results. Aside from the fact that you get stress relief if you do it correctly with different alloys. And if I may, I wanted to bring WPC into this. And one of the reasons that we love working with Izumi, and we thought that there was great synergy between us, WPC takes that to the next level at the surface. It does two things. It creates higher residual compressive strength, and it also relieves stresses at the surface. But threefold to that, what WPC does, it creates a surface that has micro dimples in it. And so when you're talking about products that need a thin oil film like crank journals, even everybody knows that pistons get sealed by the oil, not the rings themselves. All that lends into taking cryogenics to absolutely the next level in the racing industry, reduce friction, higher compressive strength, all that blends. So CTP takes care of the internals and a little bit of at the surface, but WPC adds even more. And we've worked with very large manufacturers, and when we add WPC to high wear items, they perform even better than with cryogenics.
That's impressive. Izumi, do you want to speak a little bit more on that?
Yeah, so WPC is a good process to improve the surface property, harden the surface, giving compressive stress and improving oil retention. But there's something WPC cannot do, which is improving the core material. So, but cryogenic treatment can strengthen from the core material. So align the crystal structure. And I think it's a very good combination, treating cryogenic treatment and then WPC.
That's interesting. Again, I want to remind you, if you have a question that you would like to ask either Benzion or Izumi, just type it into the chat and we'll certainly get your questions out there as well. When it comes to parts that require a bit of machining, let's say we're talking about engine blocks or something like that, does someone send you the final block, it's machined, it's honed and all of that for the cryogenic, or is there a different part in the step where this comes into play?
Right. So, it all depends. The challenges we run into is if you're doing a block and you're selling it from far away, you don't want to send it twice. So the honing is actually much better after cryogenic treatment. We've tested bores that were rated at 32, 35, 40 HRC, etc. And when you actually test the bore all over, up and down and around the circumference, you notice that you're not getting the same readings before cryogenic treatment, and afterwards you're getting the same readings. So we get parts that typically things like gears that people want to rem, we get them to cryogenically treat before they rem treat them, because they say they could actually, with the naked eye, see the difference in shine. And that goes to speak to the uniqueness of what the process does. It actually makes the surface that much better. So if you wanted to, you would do your rough boring, okay? You would send it to us. We would relieve some of the stresses that are induced by the machining process. You would get it to whatever tense you would need to get it to. You would then score or obviously create the final honing afterwards, because that will give you a much finer surface. Ideally, that's what would happen, but you can send afterwards. It's not a detriment if you do it after your final honing as well.
Mm-hmm. We've already talked about a handful of the applications, if it comes to engine components and internals. You mentioned axles and springs and different things like that. But, if you could, in the automotive industry and the racing industry, talk about some more of the applications that where this would benefit people. Right.
So coil springs, people don't think about that so much. Suspension springs. I know we talked a little bit about, valve springs and the hell they go through, but we see a lot less fatiguing over a race distance, and therefore there's a lot less settling. So if you have a car that relies on aerodynamics and any kind of a settlement that might happen, you can prevent a lot of that during the race. There are certain plastics that respond really, really well to cryogenics. We don't know all the plastics that will survive. ABS, for instance, and that's extensive research has been done into this. No, there isn't a lot of ABS used in racing, but ABS actually becomes 30% stronger. It doesn't mean it's stiffer, it doesn't mean it's more brittle. It just enhances all of its qualities by 30%. We treat pistons with coatings on them. There's been research that was done in Japan that shows cryogenic treatment that's done after the coating is done. You get about a 30 to 40% increase in bond strength between the coating and the base metal, and that's always a good thing. TIAN or TIN coatings, any DLC actually, because it's carbon-based coating, goes up exponentially. We do this day in, day out. And even things like anything that reciprocates, we even do rims. Yes, I know it sounds crazy, but you reduce their harmonics. And again, we can actually increase the strength of alloys by quite a bit.
Wow. I would imagine too, and even talking about the piston coatings and things like that, what a huge advantage that is, especially when it comes to, the life and the advantages that those come with. All right, we've had a handful of questions come in from the chat, so I'll just throw those out to you guys and we'll continue with the conversation. And if I mispronounce any of this, please forgive me. But the question is, WPC and cryogenic treatment both have the ability to induce austenite to martensite conversions for steels with relevant phases. Can this effect be compounded by using cryo then WPC?
The conversion from austenite to martensite typically happens at cold temperatures. Okay, you can do that. You can do that with heat treat as well, but it's the most complete with cryogenics. So when a heat treater does his or her work correctly, you do get a decent amount of conversion. You get case hardening, whatever you're looking for in the heat treat that heat treat calls for that particular component. So if they're asking if it's compounded, what cryogenics and WPC does is take the alloy hopefully to its absolute optimum performance. When something goes from molten to solid and then some tempering temperatures and heat treating, once it goes into a solid form, the chains are locked in, okay, unless you reheat them and loosen them up. What we're doing is with the cold, everything just shrinks that much more. Atoms take their place where they might be missing. You're shrinking everything and you're refining it to a level that you couldn't do with heat treat, because heat treat keeps everything fluid, where cold locks everything in.
Okay, that makes sense. And does it matter process what the order is?
Yes, we first cryogenically treat and we WPC afterwards.
Okay, and can one exist without the other? I mean, I assume you can do cryogenic on its own. Can you do WPC on its own as well?
Absolutely, you can send in parts if you want to and have them WPC'd exclusively. It's whatever you want to do. WPC has existed way before Izumi and I worked together, and hopefully for many years longer. But yes, many people send in parts and all they want is the WPC, and we're happy to oblige.
Okay, and the next question, this maybe can go to this a little bit. I know Ogawa mentioned cryo treat before WPC is recommended, but has anyone successfully used cryo? Well, it says cryo heat treat, but I guess cryo treat after WPC.
Yeah, I mean, we find that it's the most optimum at the end of the day. But if you have a product that's been surface treated by us or anybody else, you can send them in and have them cryo treated. It's not detrimental, but for us, it's the most optimum.
Okay, that makes sense. And what is WPC? Is it an acronym for something? Like, what exactly does that mean?
Izumi, I'll let you take over.
Yeah, WPC treatment. WPC originally stand for wide pinning cleaning. WPC has a wide application, and it's a pinning process. C means cleaning, so it can clean the parts. But after that, some Japanese top company who knows very, he has a lot of knowledge, as he says, about shot pinning. So he against WPC treatment process. So we changed the name to Wonder Process Craft. It's a strange name, but we removed pinning because at the time, it was maybe over 30 years ago, they don't believe like powder. We use very fine media, which is like powder. So the impacting the powder won't make any big difference. At the time, it was thought like that. So that's why we removed pin. So now it's Wonder Process Craft.
Okay, no, thank you for that. And a great explanation too, especially the evolution of all of that. All right, another panelist question here. Can you explain the difference between WPC or Cryo to DLC coatings and the advantages?
Okay, so DLC has its advantages. It's an incredible coating process. But remember, coating is just that. It's just the coating. So once the coating wears off, you're left with the base metal. So now if you use cryogenics and you increase the bonding strength of DLC to the base metal, Izumi and I actually cryogenically treat parts, we WPC them, and then they get DLC'd on top of it. So you have the oil retention capability of WPC, the higher compressive residual strength that you get from WPC, the strength of the base metal, and then you put your DLC on top of that, and now you've got a complete process. We don't pretend like we're replacing something else. There are a lot of great coatings out there. DLC happens to be one of them, but the price of DLC is quite steep. Not everybody wants to DLC everything, and therefore you may not have to DLC all your components, but I think you should be thinking about cryogenically treating and WPC treating everything, all these components, because the cost factor and the benefit we feel is just as good, or well, actually better when you combine the two.
Mm-hmm. Okay, thank you for that. And the next question, let's see. Oh, hang on a second. These are starting to scroll everything up. So let me make sure I try and get everyone in order here. Any technical literature or research or recommendations for cryogenic treatments for further metallurgical understanding? If someone wants to do some of their own research and find out more, would you direct them somewhere?
Yeah, so the Cryogenic Society of America has a pool of research papers that we actually contribute to all the time. Cryogenic Society of America has been a great ally of ours. Obviously, they want to promote the process. They cover the entire field of cryogenics and even cryonics. Cryonics meaning freezing biological matter. But yes, Cryogenic Society of America actually has a website where you can go on and actually read a bunch of research papers. Like I said, every year we contribute, we find new research papers, and we post them up there.
Okay, that's great to know. All right, does your cryo process include a high temp normalizing process to the actual cryo process?
Right, so because Izumi and I build our own machines, they're unique design, we actually include tempering temperatures. We're able to put heating elements inside the machine, and we encourage tempering. Not everything needs to get tempered. We recently discovered that you get much more strength out of 300M if you know how to not temper, or temper at different times. So we worked with a lot of the off-road industry, and a lot of their axles and CVs are 300M, a lot of components, because 300M is so fantastically strong. And so we tried to work with that alloy quite a bit, and we found how to maximize its results.
Okay, that's interesting. All right, this goes back to the martensite and austenite. Can you estimate how much more martensite is converted from austenite using the cryo process versus not performing the cryo process?
We're talking about, from the research papers that I did read, probably up to 50 to 60% further conversion.
Wow, that's impressive. All right, this question: cryo works for aluminum. Does cryo work for aluminum? And maybe even if you can expand on that, you had already mentioned a couple of different types of metals. Just sort of a little bit of a range of what really works and what application.
Right. So cryogenics does work on aluminum. We get a lot of parts from aerospace, mostly 6061 T6, 7075, different heat treatment. Almost anything that goes up into space, bar none, that is either made by a subcontractor for NASA or NASA themselves, gets cryogenically treated one way or another. They precondition it, they stress relieve it, and if it goes up into space, the rigors of space are great, and everybody knows that. And 90%, 99% of what we get are aluminum alloys.
Interesting. All right. Any experience or data available regarding using WPC and/or cryo treatment on high-strength fasteners, for example, 8740 or H11 materials?
We do that quite a bit. We get a lot of fasteners from different industries, of course, especially airframe manufacturers or airframe fastener manufacturers. In fact, we recently made a machine for a manufacturer so that their tools and their fasteners will last longer.
Okay. Yeah, and in fact, while we're even talking about that, as far as who uses the tech today, you talk about aerospace, you talk about manufacturing. Obviously, we're talking about automotive and motorsports, but who else uses the tech? Where does it apply?
Many different industries. So what we find is manufacturers don't always want their products to last a lot longer to the end user. There is planned obsolescence with anything. Obviously, some people less, some people more. We do find some manufacturers are still purists in their approach. They want the best product out there that they can have. But the manufacturing process itself, whether it's Eaton or anybody else out there, big manufacturers. So back in the late 90s, Remington Firearms used our machine and our processes. They saved, I think from their reporting, over $1 million to $1.2 million a year in manufacturing costs. Winchester, another company that saved over $1 million with our process and our machines. FN Herstal bought Winchester, bought a machine, took it to Belgium, and then produced a research that showed that TIAN coded cutting tools were 400% more effective than not treated. And they actually sent us the paperwork. We have it. We can share it with other people.
Wow, that's a big number right there. All right, getting back to some of the questions. We cryo treat a lot of brake discs and see significant benefits in wear rates. Have you also seen this?
Absolutely. Me personally, we treated, we're out in California, we treated the entire Kern County Sheriff's Department brakes at some point. We supplied the rotors that we were sourcing, as well as pads out of North Carolina. We actually also treat the pads. If they're semi-metallic, they will actually last anywhere from 200 to 300% longer. The Kern County Sheriff's Department, by their admission, nothing's written down, of course, but on 500 vehicles, they saved $500,000 a year. They were typically getting, with other major manufacturers, anywhere from 12 to 15,000 miles per set at 50% wear, because they're critical vehicles. They take out the rotors at 50%. We gave them 80,000 miles per set.
Wow, that is impressive. Are there any other benefits in a part like that? Is there anything improved in braking performance, or is this more just a longevity gain?
Yes, you do see improvement in braking performance. You actually see a more rapid cooling. And we think it's because we're refining the grain structure. Heat finds its way out a little bit faster. We've seen tests where we've taken, thermocouple readings off of a race car. On the right side, they had an untreated part, left side treated part, and we saw a good reduction in heat dissipation. And also what we're hearing from some of the people that we treat stuff for, and especially in the racing industry, is better feel, better modulation, better feel.
Yeah, which that's pretty essential and important, I'm sure. A lot of questions here. This is a pretty active audience today, which is just wonderful. I heard that depending on the alloy cryo treatment can result in toughness decreases of certain alloys. Is there any truth to this? And is it more simply a function of martensite fraction?
Right. So there can be a reduction in what they call a little bit of toughness. But what we find is, and what we've seen also, whether it was research and or, excuse me, and or practical results, you may get a reduction in one area, but you get a vast increase in so many of the other components that are working so much better, so the part already lasts longer. So, case in point, ring and pinions. Right, you might see a slight reduction in what they call toughness, but everything else improves exponentially. Daya Sihara, Formula Drift champion, Formula Drift champion, I think last year, not this year, took the Pikes Peak in his class, and they were going through ring and pinions. I think 3 ring and pinions before they went and installed a Cryo and WPC set in there, and then one with that. And when they took it apart, it showed almost no wear, and that's a big factor.
Yeah, that's a huge change. A question about titanium. Does cryo work for that?
Absolutely. So all alloys see a gain. I want to go back a little bit to the point that I was making about being able to understand what the alloy needs. And it's, humans have been heat treating metal in all kinds of forms for about 7,500 years. We've only been able to use these types of cold temperatures for about 100, 110 years. So there's still a lot to be discovered. So time and temperature and processes are very, very, very touchy. You might get something to perform great at, let's say, an 8-hour sort time, but other things may need more than 30 to 40 to 50.
Okay, here's another one. Your recommendations in terms of using cryogenic heat treatments between your quenching and tempering, or using after tempering?
One more time, please. Sorry.
It says, what are your recommendations in terms of using cryogenic heat treatments between your quenching and tempering, or using it after tempering?
Yeah, so you want to finish up. You want to finish all your heat treatments. Okay, the reason we temper is we know we're locking in the results after cryo treatment, right? So we're tempering at a fairly low temperature. We're not affecting the temper, the case hardening that a lot of people are looking for in heat treating. We're not affecting that. Okay, so you want to get all your heat treatment done, and then you want to cryo treat and temper, or either we temper or we don't temper, depending again on the alloy. But I want to make a point here with heat treating. Cryo cannot replace heat treating, ever. Heat treating must be done, and must be done at a very high level for the component to actually survive. We've seen, we worked with somebody back in the mid-90s. They created a very unique lightweight axle that they designed. They were shattering the axle prematurely. We cryogenically treated it. It lasted maybe 10, 15% longer, but what we noticed was the heat treater was doing creating a problem with embrittlement. When that got sorted, everything else worked itself out.
Okay. This question says, we've gone over the facts. What are the myths? Or are there some myths out there that you want to dispel?
Yeah, people think that you create embrittlement, right? You make things a lot harder. Well, you're not changing the specific gravity of the product, right? So it doesn't become bigger, stronger. And to that point, we don't change tolerances unless the part is so stressed that the cryogenics actually stress relieves it, and then it actually warps into its stress. So if you have a component like that, yeah, you might have some movement. But anyway, I think that I answered that question. Sorry.
Okay. Oh, no, that's great. Do you deal with very low volume clients, say trying to cryogenically treat project car components? If I'm an individual and I have a small batch of things.
Absolutely, absolutely. We have a $300 minimum. Okay, that saying that $300 does cover a little bit here. We get cranks, we get valves, we get springs, we get retainers. As long as that minimum is met, we're more than happy to help people out, and sometimes a little bit less. We try to be as accommodating as possible. There are a lot of people out there. It's not just industrial clients, although we do very well with industrial clients. We love people that send in good parts, clean, of course.
Clean. All right. I like that. When treating finished parts, either steel or aluminum, is there any risk of distortion from the cryo processing? I know you spoke a little bit about this, but if you would answer that one.
Right. So you do, I'd say 99.9% of the time, we do not distort anything. Okay. The only time we've seen distortion is one, the heat treatment was done poorly. The product contained a lot of stresses, and so it warped into its stresses. And at that point, if you would have put that component into your car, let's say a cam, and it heat cycled a few times, it would have warped anyway. So you really want to know. And to the point, we get used gears sometimes, and those gears, when they're used, they go through a lot of stress. Recently, we had a gearbox, 6-speed gearbox come in, and between the Cryo and the WPC, there was a little piece that chunked off on the end of one of the gears. I want to stress that that is probably a good thing. And the reason is there was probably a fissure under the surface that showed itself up after the extreme temperatures. And again, the WPC, you want to know that that part is faulty. We're not happy that it happens, but it's a good thing. You don't want a piece chunking out while it's in use.
Yeah, I was going to say it's way better than that happening while it's not rotating under load. So is it fair to say then, bad parts in could mean bad parts out, but good parts in will be better parts out? Right.
I have an old saying. I hope it's okay to say this. You can't turn a donkey into a stallion. You can take a well-made part. It doesn't have to be a stellar part, but it has to be, engineered correctly. We've had people call us and say that they're building out a diesel motor. They're tripling the torque, tripling the torque, and they want us to treat the output shaft. I won't take that part. I don't want people saying that Cryo doesn't work. A part like that has to be designed correctly to take the load, and will take it much further than much further than it would typically go had it not be cryogenically treated or WPC treated.
So when you do this, you talk about the gearbox, you're taking like complete assemblies and treating it all at one time as opposed to its individual components. Is there anything, if an assembly uses different types of metals, let's say, is there any concern there? Do things expand or contract or whatever in different that would be impacted by cryo?
Right. So we don't want anything that's one part pressed into another part. Contraction and expansion rates can differ greatly. Aluminum wants to move all the time, steel less so, iron even less. Payloads with iron take a much longer time to reach their absolute core temperatures. And if I can make a side point here, we use thermocouples in the machine. We put thermocouples on parts that are sitting on the bottom, in the middle, and the top. What's important is that your component reach the temperature that you want it to reach, not the air temperature inside the machine. So this is all the scientific. So we were recently at Bryant Racing Cranks, and we saw them putting thermocouples on all their cranks that they were heat treating, and that's same goes for cryogenics. You want to know your core temperatures. You want to keep the part there at those temperatures and play with those temperatures. So hope I answered that question correctly.
Yeah, no, you did. A question here asks about next-gen aerodynamic materials and your views looking forward, and maybe even if you can talk about advancements that are being realized even now.
Okay, sure. Izumi and I have thought a lot about this, and we discussed this extensively. We'd like to be able to shorten up the time that it takes to do this. Our longest treatment is over 90 hours. It's quite a bit, it's quite long. So we're doing a little research, and we're quite active in trying to create the best treatment we can in the shortest amount of time. But we also think that there's a lot that can be applied here. You know, who says that what we're doing in cryogenics today is the best? You know, if you don't think ahead, you're never learning. So we'd like to think that we're advancing the business and trying to make it even better. We might be able to do that, but it might take time. But we're recently, like I said, we made a discovery how to treat aluminum alloys, and you know, probably a 40% increase in rigidity in aluminum alloys, which is a big deal.
Yeah, that is. Cryo treatment seems to usually be done using liquid nitrogen. Is it possible to use other medium like helium? And is there any value in doing so?
Right. So helium is gets as close to absolute zero as you can get. Some aerospace companies require helium treatments, and we do them. Helium is about 13 to 14 times the cost of liquid nitrogen. So you can imagine a payload of helium is going to cost quite a bit of money, which only aerospace companies are willing to invest in. So helium will take you, we typically treat helium treatments at negative 430. It's not always advantageous though to treat with helium. At negative 430, sometimes you don't get the same effects as you get at negative 310. And I'd like to touch up on the fact that our machine, because of the way it's built, we're able to hold temperatures of negative 308 to 310 cost effectively because we use vacuum insulation. We have seen over the many years that there's a marked difference between holding at negative 299 to 300 and even 308. You're seeing sometimes a 20 to 30% increase in performance by holding at those temperatures.
Wow. And you know, you talk about you build your own machines and, you know, the things that you do to continue to advance it, but where do you see the process going from here?
Well, everybody uses heat treatment. We'd like to standardize heat treatment along with cryogenics. And speaking of heat treatment, we see a lot of heat treaters throw parts into liquid nitrogen. And I mean immerse them into it. This isn't a quenching process. This is, you know, you thermally shock a part when its surface and its core is sitting at 60 degrees, and then you throw it in and it goes right down to negative 304, but it goes down to negative 304, 305 at, you know, with just at the surface. It takes time until the core gets there. So you're creating a lot of micro fissures and a lot of stresses along the way, which you're trying to prevent with, you know, cryo in the first place. So we suggest that if you're going to get cryogenic treatment and you're going to have it done, we suggest that you have it done with and know what you're getting done. Ask questions, ask what they're doing, what their process is, and so on. Not everybody's going to tell you their time and temperature ratings. They should tell you what their ultimate temperature is achieving. They're not always going to tell you ramp down and ramp up at soak times, but you should, because there isn't a book and there isn't certification. We're trying to get NADCAP certification now, but NADCAP, they don't understand what cryo is. So we have to sort of teach them and get certified that way.
That makes sense. Benzion, Izumi, this is one of the most fascinating webinars that we've done, and without question, one of the most active when it comes to the questions, and really fascinating to learn about what you do and the benefits of it. And we appreciate you today.
Thank you so much for having us.
Thank you very much, Izumi. And Ben, I'm a big fan of Izumi. I've known Izumi for over 20 years, and we have a long history together, and I really pushed him hard for the last 2 years, and you've got to come on the webinar series, you know, and he wanted to wait, you know, for Ben to be able to join, and what a great webinar. So thank you very much for being with us today. This webinar has been recorded. It will be posted later on the ePortrait platform, distributed through our different channels as well as our newsletter. We will be back next Wednesday with Pack Racing Springs. We're going to be talking valve springs. So again, thank you very much. In the meantime, enjoy the platform. We build this ePortrait platform for you, for the industry. It's open 24/7, 365. Take advantage of it. Let's go racing, and we'll see you live next week. Thank you very
so
much.
Thank you.
Bye-bye.
Registering on ePortrait is easy. Fill out your name, email, phone number, and create a secure password. Next, select your business type. Choose supplier if you're looking to display products or services and connect with buyers. Choose racing business if you're looking to find new parts and connect with suppliers. Choose race team if you own or are a member of a professional racing team. Begin typing your company name. We most likely already have your company in our database, which you can select from the drop-down. Then, enter your job title. Choose Claim Company if you'll be editing your company profile. Other members of your company can choose Join Company if they'd like to use ePortrait as well. You can view and agree to our terms of use here. If you'd like to receive our weekly newsletter, choose Accept. Click Register Now, and your registration will be submitted for approval. You'll need to confirm your email once it goes through. To keep our platform industry only, you'll be approved shortly after. If we require additional proof of business, we'll reach out. Welcome to ePortrait.